Look around you right now, really look. The chair you are sitting on, the screen you are reading this on, the coffee mug within arm's reach, the clothes on your body. Every single object surrounding you was manufactured somewhere by someone using processes you have never seen and probably never thought about. 3 centuries ago, you would have known your local potter by name. You would have watched the tailor cut fabric for your coat. You would have seen the blacksmith forge your tools. Manufacturing happened in front of your eyes, performed by people you trusted. Now it happens invisibly, thousands of miles away. Behind factory walls you will never enter, in countries you may never visit, performed by machines and workers you will never meet. This disconnection is not just an inconvenience, it is a crisis hiding in plain sight. Because when production becomes abstract, so does accountability. Electronics containing conflict minerals, fast fashion flooding landfills, carbon footprints too massive to calculate. We cannot fix problems we cannot see. We cannot demand change for systems we do not understand. What you are about to learn will transform how you look at every object around you. And once you see the hidden machinery behind everyday things, you cannot unsee it. Remember March 2020? When toilet paper became more precious than gold? When people fought in supermarket aisles over something they had taken for granted their entire lives? That panic-buying frenzy revealed something most of us had never considered: the remarkably complex network behind even the most mundane products. Next time you are in the bathroom, take a single square of toilet paper and really look at it. That 10-centimeter square with its perforated edges and embossed pattern represents one of the most intricate global operations you will ever hold in your hand. Your toilet roll's journey starts in managed forests, specific tree species harvested on carefully planned rotation cycles spanning decades. Logs transported to pulp mills where they are chipped into small pieces, cooked with chemicals to break down the lignin, washed repeatedly, bleached. Solid wood transforms into fibrous slurry. That pulp gets pressed onto massive heated rollers. Machines squeeze out water. High temperatures dry the material. Everything winds onto enormous parent rolls weighing several tons each. But those giant rolls are not what you see in stores. They ship to converting facilities, specialized factories where the real transformation happens. Industrial machines unwind the giant rolls, run them through embossing rollers that create texture and thickness, perforate them at precise intervals, rewind everything into the consumer-sized rolls we recognize. Different products need different setups. Quilted patterns require specific embossing cylinders. Extra soft versions use gentler tension. Recycled paper needs adjusted chemistry. Each variation means reconfiguring equipment. Then comes distribution. Finished rolls get packed, palletized, sent to regional distribution centers. From there, allocated across retail channels, supermarkets, convenience stores, bulk retailers, each with their own ordering systems, delivery schedules, inventory requirements. Retailers forecast demand based on historical data, coordinate with dozens of suppliers, manage just-in-time delivery to minimize warehouse costs. The system runs like clockwork, until it does not. The pandemic demolished this carefully balanced system overnight. And here is what nobody understood at the time. Commercial toilet paper and residential toilet paper operate as completely separate industries. Different manufacturers, different converting equipment, different packaging lines, different distribution networks, different purchasing contracts. Those thin, giant rolls in office bathrooms and the soft, quilted rolls in your home come from entirely different worlds. When everyone suddenly worked from home, demand shifted massively from commercial to residential channels. Tens of millions of people who used to use toilet paper at work were now using it exclusively at home. But you cannot just redirect a jumbo roll meant for office dispensers into grocery stores. The machinery that makes them is different. The trucks that carry them are different. The warehouses that store them are different. Even the buyers who order them are different. Manufacturers could not simply flip a switch. Retooling production lines takes weeks. Redirecting supply chains requires renegotiating contracts. Creating new packaging formats needs different materials and equipment. Meanwhile, panic buying amplified the problem exponentially. People were hoarding residential toilet paper while commercial stockpiles sat unused in empty office buildings across the country. The toilet paper shortage was not a manufacturing failure. It was a visibility failure. Nobody understood how the system actually worked until it stopped working. That humble roll of toilet paper is actually one of the most remarkable objects you will ever encounter. And it is one of the simplest things we manufacture. Imagine a chocolate chip cookie. Whether homemade or bought from the supermarket, the basic manufacturing process is the same, right? Flour, butter, sugar, chocolate, bake. Not exactly. That cookie could be the result of vastly different manufacturing processes, each with its own logic, trade-offs, and complexity. Every factory, regardless of what it makes, does essentially the same thing. It takes inputs, raw materials, energy, labor. It uses specific processes involving people, methods, machines, and materials. It creates outputs, the end product. But how this happens varies wildly depending on scale. Start in a home kitchen. Ingredients measured by hand, mixed in a bowl, scooped onto a tray, baked for 12 minutes, one batch at a time. Total control, infinite customization, but limited output. Labor-intensive and slow. Step up to an independent bakery using batch production. Now we are talking industrial mixers handling 20 kilograms of dough. Programmable ovens baking multiple trays simultaneously. Each batch is still distinct, allowing for variety. Cranberry orange 1 hour, double chocolate the next. Higher volume than home baking, but still significant hands-on work between batches. Scale up further to a mass production facility. Continuous production lines dominate. Dough gets extruded mechanically, deposited onto conveyor belts at precise intervals, travels through tunnel ovens maintaining exact temperatures across zones. Thousands of identical cookies baked per hour. Minimal labor required per unit. The trade-off? Flexibility vanishes. Changing recipes means shutting down lines, adjusting machinery, recalibrating systems. Every variation costs time and money. Finally, consider the sugar refinery supplying that cookie factory. This is continuous flow production at its purest. Raw sugar cane enters one end. Refined sugar exits the other. 24 hours daily, 7 days a week. Stopping and restarting would be prohibitively expensive. These plants run constantly, optimized for absolute consistency and maximum volume. They cannot pause, they cannot experiment, they just run. Understanding these distinctions changes how you see the world. When you grasp how scale shapes production, you understand pricing. You understand why certain products exist and others do not. You understand the genuine complexity behind everyday goods. Manufacturing is not magic. It is an intricate set of deliberate choices weighing efficiency, variety, and volume. Now, consider something more complex than toilet paper or cookies. Consider your phone. That device in your pocket contains components from dozens of countries. The processor was designed in California and fabricated in Taiwan. The screen comes from South Korea. The battery minerals were mined in Congo. The camera lenses were crafted in Germany. Final assembly takes place in China. Each component requires its own manufacturing journey before they all meet in one factory. Hundreds of suppliers, thousands of workers, millions of individual parts, all converging perfectly so you can scroll through social media. Still seems manageable? Try an airplane. Airbus has spread production across an entire continent. The main assembly plant sits in Toulouse, southern France. Engines arrive from General Electric in America or Rolls-Royce in Britain. Wings get built in Wales. Some are over 35 meters long. They get loaded onto specialized aircraft called belugas and flown to Bremen, Germany, where the flaps and slats are installed. From there, they fly to Toulouse for final assembly alongside fuselage sections from Hamburg and tailpieces from Spain and landing gear from France. A modern commercial aircraft contains roughly 2.5 million parts. 2.5 million. If one part malfunctions, engineers cannot just swap out the faulty component. They need to trace back through the entire supply chain. The network of suppliers, manufacturers, and logistics companies. Where did the problem start? Was it the raw material supplier? The parts manufacturer? Something that happened in transport? Dizzyingly complex, right? Let us look at something simpler, ice cream. Except ice cream has its own hidden complexity. Because from the moment ice cream is made, it must stay frozen below -18 degrees Celsius at every stage. Factory to truck, truck to warehouse, warehouse to store, store to your freezer. The danger zones are the handoffs. If ice cream warms up even slightly and refreezes, it becomes icy and grainy. The texture is ruined. The product is ruined. Trucks pre-cool before loading. Warehouses maintain freezing temperatures constantly. Sensors monitor everything. One mistake anywhere in the chain destroys the product. These systems work remarkably well, until they do not. A single supplier shutdown, a blocked shipping route, an unexpected surge in demand. Any disruption can cascade through the entire chain like dominoes falling. Your phone's production halts because one Taiwanese factory floods. Ice cream spoils because a refrigerated warehouse loses power for 3 hours. An airplane sits grounded because a specialized bolt manufacturer cannot deliver. Understanding this fragility matters. It explains why shortages happen suddenly. Why just make more is never simple. Why sustainability efforts face genuine obstacles beyond corporate goodwill. Next time you encounter a product shortage or price spike, you will recognize what is really happening, not failure. But the intricate machinery of global manufacturing straining under pressure, it was never designed to handle. Manufacturing works best when everything is logical, systematic, predictable. But customers are none of those things. They are fickle, surprising, maddeningly unpredictable. Figuring out what people want, when they will want it, and how much they will buy is genuinely one of manufacturing's toughest challenges. Get it wrong and the consequences are severe. Nokia famously underestimated smartphone demand and clung too long to feature phones. They went from dominating the mobile phone market to near irrelevance within a few years. Meanwhile, Nintendo's Wii was so underproduced that shortages lasted for years. They lost billions in potential sales, not because nobody wanted the product, because they could not make enough of it fast enough. Sure, companies use data to forecast. Cadbury knows exactly how many cream eggs sold over the past decades. They can make educated guesses about how many to produce each Easter. But there are no guarantees, which is why manufacturers have developed clever strategies to hedge against our irrational behavior. Counter-cyclical products deliberately exploit how we want opposite things at different times of year. Lawnmower factories make snowblowers in summer. This keeps equipment and workers productive year-round, while customers predictably shift between seasons. Level production works when customer preferences stay steady, but purchases do not. Pasta makers and pen manufacturers run factories at constant capacity. They build inventory during slow periods, because we will always need pens eventually, just not necessarily this week. Demand chasing accepts that some customer behavior is genuinely unpredictable. Fashion retailers like Zara live this way. They hire temporary workers, run overtime, respond to trends within weeks, because you cannot forecast what people will suddenly decide looks good. Built-in flexibility acknowledges that customers might want different things tomorrow. Volkswagen's platform strategy shares components across dozens of models. The same factory line can pivot from making Golfs to Audis based on which happens to be selling better that month. Manufacturing might love predictability, but it is customer chaos that keeps the whole system moving. That satisfying click when your electric kettle switches itself off? That tiny sound represents a genuine breakthrough in everyday safety. A breakthrough most people have never considered. Before 1970, kettles were metal, either stovetop models heated from below or standalone electric versions with heating elements. By the 1920s, the element sat submerged in water, but nothing told the kettle to stop. Left unattended, it would boil dry. The heating element would burn out. Inconvenient, but manageable. Then came plastic electric kettles in the 1970s. Left on after boiling dry, these did not just burn out, they melted, creating genuine fire hazards. Enter Dr. John C. Taylor, who invented the automatic cutoff switch using a bimetallic thermostat. Here is how it works. 2 metal discs with different expansion rates sit at the kettle's base. When water boils, steam channels through a tube to these discs. As they heat, one disc expands faster than the other. This causes them to bend. At a specific temperature, they suddenly snap into a curved position. That is the click you hear. This mechanical snap pushes against a switch lever, breaking the electrical circuit instantly. That is improving one object. One small innovation that has prevented countless fires and saved untold lives. But what about a manufacturing shift that could reshape the entire planet? The move from internal combustion engines to electric vehicles. Electric cars are not new. They actually outsold gasoline cars in 1900, but battery limitations killed them off for over a century. Now they are back, and they are far better for the planet. But pivoting to EV production will not be easy. Converting an existing gas-powered car to electric might sound straightforward. Swap engine for motor, add batteries, done. But designing proper EVs from scratch means completely rethinking vehicle architecture. Battery packs must integrate into the chassis as structural elements, not afterthoughts bolted on. Thermal management becomes critical. Batteries need cooling systems that prevent overheating but do not drain range. Regenerative braking systems recover energy but require sophisticated power electronics. Weight distribution changes entirely when you have 500 kilograms of batteries along the floor. Even the suspension, steering response, and crash protection structures need redesigning. Manufacturers face stark choices: retrofit existing factories, which means new assembly lines, different tooling, retraining thousands of workers, or build dedicated EV plants from scratch. Both options cost billions. Battery production alone demands entirely new supply chains. Lithium mining in Australia, cobalt from Congo, rare earth processing in China, cell production in gigafactories that must be built before cars can roll out. Then there is charging infrastructure, millions of charging points needed before consumers feel confident buying EVs. The stakes could not be higher. Transportation produces roughly a quarter of global carbon dioxide emissions. A complete shift to EVs powered by renewable electricity could cut those emissions dramatically, not just slowing climate change, but reducing urban air pollution, decreasing oil dependence, and fundamentally transforming how humans move. Dr. Taylor's kettle switch changed how we make tea. This manufacturing transformation could determine whether we successfully address the climate crisis. Maslow's hierarchy of needs places survival basics at the foundation: food, water, shelter, clothing. Here is the irony. The way we manufacture these essentials is undermining our ability to survive on this planet. And as climate patterns shift, basic survival becomes more resource-intensive precisely when resources are growing scarcer. Consider the fundamentals. Construction accounts for nearly 40% of global carbon emissions. Concrete alone contributes 8%, more than aviation. Industrial agriculture generates 14.5% of greenhouse gases. A third of all food produced is simply wasted. The fashion industry produces 10% of global emissions and consumes vast amounts of water, churning out cheap garments worn briefly, then discarded. The imperative becomes clear: manufacture things less harmfully. Manufacture less harmful things. Lean manufacturing offers one path forward. Pioneered at Toyota in the 1950s, the core insight was radical. Most manufacturing activity is waste. Not just scrap material, but any step that does not add value. Workers waiting, excess inventory, unnecessary transport, overproduction. Lean systematically eliminates these inefficiencies. Less wasted material means fewer raw resources extracted, less energy consumed, lower emissions produced. Modern examples show this working at remarkable scale. British Sugar's factories process 8 million tons of beet annually and produce less than 200 grams of waste per ton. Stones become road construction material. Soil becomes topsoil. Pressed beet pulp generates biogas for electricity. Lime becomes fertilizer. Waste heat warms greenhouses. Carbon dioxide feeds plants. Nothing leaves as waste. Every byproduct becomes an input for something else. Gianologia in Spain transformed denim manufacturing entirely. Traditional jean finishing consumed 100 liters of water per pair. Industrial washers spinning for hours with stones and chemicals. Gianologia's laser technology eliminates dye through sublimation, creating distressed effects in seconds. Their ozone washing saves 95% of water, cuts chemicals by up to 100%, reduces energy by 80%. Over a third of the world's 5 billion jeans now use this technology. Manufacturing created this problem, but manufacturing innovation might also provide solutions: smarter processes, circular systems, genuine efficiency. The challenge is not stopping production. It is transforming how we produce. Here is what you now understand. Manufacturing transforms raw materials into finished products through interconnected global systems of remarkable complexity. This complexity creates both extraordinary efficiency and fragility. Specialized supply chains optimize for predictable conditions, but they collapse under disruption. The toilet paper crisis proved this. The chip shortage proved this. The pandemic proved this over and over again. Understanding these hidden processes matters. It explains why shortages happen, why sustainability proves challenging, why the everyday objects we take for granted represent both impressive coordination and vulnerable interdependence. Every object around you tells a story of forests and factories, of logistics and labor, of chemistry and engineering, of decisions made thousands of miles away by people you will never meet. Now you can read those stories, and once you start seeing them, you will see them everywhere. In the mug on your desk, in the clothes on your body, in the device in your hand, in every manufactured thing that surrounds you from morning until night. Your life is manufactured, every moment of it. And now you understand what that really means.